next speaker is Daryl Ball, and he's going to give us a brief history on geophysics.
I'd like to thank Ken for inviting me. And, oh, here we go. So, I'll talk about this one. It's called A Brief History of Geophysics at Raglan Mine, but it's really about what works and what doesn't work for EM for nickel sulfides. Oh, that's the wrong thing. There we go. So this document contains statements that are or may not be deemed to be forward-looking statements, so I'll stop there and we can let the lawyers worry about that. Just like to go through the early history of exploration at Raglan, talk about some of the recent things we've been doing to improve our success, and then some conclusions. This picture here is early May in Raglan. That's actually a contact crew there doing some coil calibration tests. So it just gives you an idea of the terrain we're working in. Not much snow, but it can be quite a harsh environment. So Glencore is a major mining company. We have operations all over the world, and Raglan Mine is located up here in the west side of Mangaba Bay. And we ship our ore down to Quebec City and then smelt it in Sudbury. And then we send it over to our refinery in Nickelberg. So this gives you a better idea of where Raglan is and some of the early prospecting that went on. So in 1889, Albert Lowe took a ship and he mapped the coast all along the east side of Hudson's Bay here. And when he came across this area, he noted that there was some volcanics and sediments that were located in that area. We actually have a map up at our office in Raglan just showing the map from that area. And it shows the outline of the coast, but just the geology is just outlined right on the coast, and it doesn't go any further inland. And then a group went up in 1932, Murray Watts, and mapped all that area that's outlined in purple. So this is the Albert Lowe group in 1889. This is from the National Archives of Canada, I found it, but Albert Lowe is down here, the guy looking the other way. So I figured he's a geophysicist because he was using a compass to navigate his way up the coast. But it's a pretty good, cool picture there. So this is Zero Night Prospecting Company. It's another photo I found in our archives. And it includes Murray Watts there in 1932. So they were up there going up the coast as well, and that's when they did their mapping inland. So after nickel was discovered in Thompson in 1956, they went back to this area. They actually did some airborne reconnaissance as geologists and just looked for showings around, and that's when most of the showings around Katnick and Raglan were actually discovered in 1956. So that really got interest in the area going. Then these guys showed up in 1957. So that's actually a aircraft from Spartan Aero Services, and I found it's on the web, so it's not really a Raglan picture. So don't believe everything you see on the internet. But this is probably an aerial reconnaissance survey team that were doing land surveying or air photos. So Spartan Aero Services bought 24 of these aircraft in the 50s for $15,000 each and started flying around, and that's. So this is the type of survey they were doing. It's a frequency domain EM survey, and they were flying at about quarter mile line spacing, and they basically covered the entire Cape Smith belt, and they were looking for those types of anomalies. So the sharp anomalies were steeply dipping conductors, and it goes all the way down to flat line conductors. So the Raglan property here is the area that's outlined in the white. But you can see they covered a lot of ground over by Canadian royalties that Cersei was talking about yesterday in the talk. And it's in, I'll just get my notes here. So in the report they mentioned that it was unlikely that the sediments would be conductive enough to produce electromagnetic anomalies. And as you can see, there's quite a few anomalies there. And if you zoom in, there's a couple showings here. This is our mine 3, this is mine 2, and this is the showings at Catton. These are the ore lenses that are within 100 meters of surface. So you would hope that some of these anomalies that we're seeing were directly related to the ore that's on the ground. But at the same time, there's a lot of conductors to the south here that are also showing up, and some of them are missing. But you want to remember in 1957, they were just basing their surveys on topographical features, and so they had a lot of trouble locating exactly where they were, where the airborne surveys produced anomalies, and then following that up on the ground. So they would follow up on the ground with an early Maxman type of survey. And you can see the showing number 2 here is actually a Dawson showing that's mapped on the ground, and they would go down onto the ground, put in baselines and survey lines, and then do the Maxman surveys. And also, they would also do mag surveys at the same time. So with the magic of geoscience analysts, I'm able to bring in the current database and take a look and see how they did. So this is the drilling that Asarco did in 1957, and superimposed on that is the ore lenses that are from our database. So they missed this guy. They got this nailed down pretty good. And it's interesting that the drill hole trace from the PDF here is going in this direction, and all the other drills are going north-south here. So when the data from 1957 was brought into our drill hole database, the geologists didn't get this azimuth right here. So it's an error in our database, so some of the old guys got it better than we got it. So, and the geologists still haven't fixed that hole, so I should go in there someday and fix it myself. So in 1961, it's the Bell G2 helicopter, and they flew this is one of the first comprehensive bank surveys that we did. And this is the PDF of the survey, all the contour lines superimposed on our property. And this is the mag results from 1996 geotemp survey, showing the total magnetic field. Most of the Raglan deposits are along this trend right here. We also have some, the Cross Lake occurrence is out here. And Donaldson is over in this area, and this is the endowed area right through there. So if we zoom in on that, you can see the results of the contouring overlaying the geotemp data. So you can see down here, there's a bit of an offset where the mag high is. It should be a little bit lower down here, but the sills that are up here were, the correlation is actually quite good. So it just goes, once again, shows you some of the errors that we were seeing in the early surveys with respect to locating things before. We take GPS for granted now, and I don't understand how difficult it was for them to correlate things on the ground at that time. So they did a fairly good job, and all this contouring. There's another survey that they did, and computer contouring cost more than the survey did, so. So this slide here shows us a summary of what went on before the decision to go ahead with production at Falcon Ridge in 1994. So this is what the surveying looked like. So the bar here is the resources, and so we're up to about 10 million tons of reserves, and it didn't really change from 1969 until 1993. With the additional work they did, they didn't really increase the resources at all. The average depth of the drill holes was less than 200 meters, and the blue just represents the amount of diamond drill holes that were completed. And I guess one of the most important things for nickel sulfides is physical properties. So for nickel sulfides, we operate in a very high range, and that's one thing that we can really use to take to our advantage when we're doing time domain EM, is if we're able to measure in the on time, then we can capture those high conductivity ore types. So when you measure in the off time, there is a possibility that you could be blind to detecting some of those types of responses. So Richard went over some of these things. So in the early time domain systems, we did the transitions from analog to digital. And in about the early 80s, or actually it would have been the late early 90s, there was some work done in Sudbury with Tony Watts and other people looking at the off-time responses they were doing in boreholes, and they were missing some of the rich deposits because they were just chasing the decaying responses. And so that led, at that time we were doing some drilling around nickel rim depth, and the holes were down about 3 kilometers, and Chrome would go in and do a survey, and then Lamotang would follow up with another survey. So they would spend a lot of time surveying these holes and taking a look at the different responses. So at that time, Chrome developed a technique to measure the step response. And as you move through the 80s, the time domain systems started surveying at lower and lower frequencies. And so this is I looked at all the airborne surveys that we did. So we have Digem and Geotem and others, but one of the only surveys that was available that was able to measure in the on time was the Aerotime survey. So it was able to resolve some of these high conductive responses, whereas most other systems are just measuring the off time, and they can miss these very conductive bodies. So this is an area around Mine 5, Zone 5-8, and you can see, and this anomaly picks it up quite well, and this one is missing it. And I think I'm looking down about 200 meters here, so these 3 lenses are deeper than the ones in this area. You can see that the sediments are still picking up quite a strong response in this area. And I haven't gone back and looked at this going on, see what's going on there, but nice response there in the proper ultramafic rocks. This is basalt up here, and this is some gabbro. So even with Aerotem, it still requires the geologist to go through the data and make sure that all the unknown conductors are still being accounted for. So the other technique that proves quite successful for us is Make 3D. So this once again is Mine 3 and Mine 2 that we were looking at earlier, and this aerial photo, and total magnetic intensity. And then that's the magnetic isoshells and all the ore at mine 2 and all the ore at mine 3. So you can see for us this is just a simple unconstrained magnetic inversion, but you can see how I'm not able to spin it around here, but it tracks, the isoshell tracks the known lenses quite well, and it works really well for us at Raglan. And that's a bit of the ore over here at Katnick, one of our other zones. This is, Ken was mentioning this to me the other day, but this is the squid development that Tony Watts developed with CSIRO. So Falconbridge sponsored the development of these squid sensors, and I think we spent about $150,000 developing that, and then we got exclusive use of it for a few years. And this is some of the results from the late time squid. This is what we call zone 13-14. This is one of the lenses. What we're looking at is the depth from the surface. So this lens out here is down about 600 meters, and we'll look at that through some other techniques that we're looking at. But you can see down to about 250 meters, you can imagine that this gridded product here is picking up this lens. But it's as you get deeper and deeper down trend here, this one isn't being picked up and that one isn't being picked up as well. But we're also getting some like bullseye anomaly here that they drilled, and there was nothing, no explanation for that anomaly in that case. So this is really our bread and butter as we chase these lenses down depth, just doing boreal EM surveys. And the main ones we use for the on-time systems is, we mainly use chrome, but the other two that are available are Lamotang and SJ. And Lamotang has a sawtooth that basically induces a square magnetic wave, and Sid can measure 100% duty cycle, and then Crone has the ramp, and then the spike in the off time there. So that's basically the RS1 response, as they call it. And then this is actually the one we were looking at previously, or this lens here. This was a series of drilling that was done as we were heading down dip, and then they stepped out 100 meters and they got this nice S1 off-full response here. So this is actually the discovery hole for lens 14F. So we modeled that with the 240 meter by 120 meter plate that turned into this 3 million ton lens. And as I said, this is the same response that we were looking at there earlier. So just a nice S1 off-full response. And then as you get into the lens itself, these are in-hole responses, and then when we went up depth, this is an off-hole response. But this has all been drilled off, but I just wanted to show you a profile going through the lens and the different types of responses we got. But if it was just a simple off-time system, I don't think we'd see those sort of responses. And there's another technique. So I had to put a picture in of the Northern Lights. It's been a tough couple of years doing MT surveys with the lull in solar activity, so hopefully we're at the bottom of that cycle and we'll start picking up again. So this is part of the program we did with Quantec, and we had another contractor up there as well at the same time, Dave Goldak with the Impulse. And this, once again, this is lens 14F down 600 meters, and we've got a resistivity low here that we picked up quite well, and you're also seeing it not quite as good, but up here as well. And so MT can be quite useful for picking up these lenses at depth. We also use it in submarine with some success to see even a deposit like Norman West, and that's down 2.5 kilometers. So depending on where you are in what's going on. And there were you guys from Northern West were here at PDAC with their core. I don't know if anybody saw that at the core show, but it's a nice looking ore. And this is what things look like today. This is all the way up to 2019. I sent this off to Tony Watts, and he mentioned that things had leveled off since 2010. I thought I was looking more at the graph like this way, but he was looking at it like that. So. But what's notable here is the light green is the average drill hole depth. So you can see how that's increased. We managed to stay ahead of the mill and keep on increasing the reserves as we go through production year by year, and we also have the number of drill holes drilled there. So this is something that we've just done recently. It's a type of survey. The lines we're looking at here are 3.4 kilometers long, and we're measuring segments of the line in 1 kilometer segments. We move the loops 200 meters, reread the line, and so we end up getting 5-fold coverage. So what that does for us at Raglan is we're dealing with very conductive sediments, and by doing this hybrid moving loop approach, we're able to, you can think of it like a CAT scan as you're moving through the earth, and by doing this we're mitigating the effects of the regional responses. And so, and with LaMontagne you're able to read more than one loop at the same time. So by putting the coil down on the ground, you're able to read the loop that's to the north and the loops to the south. And then this is the entire package here with 3.4 kilometers of coverage. A nice crossover here above the lenses, and at the bottom is the response from the loop that's to the south, so the reverse coupled component. Then what Eve wrote a program to forward model this, because to take a 3.4 kilometer section and run an inversion on that, with 50-meter cells, you'd probably have to wait a couple of years in order to get a decent result, and then you'd have to do it all over again. So what Eve came up with was a method to take a series of shapes and run it through the model space and do a forward model on each one of those positions, and then you would produce what we call a confidence plot. And it would, where you have good correlation, you get a higher confidence, and when you get poor correlation, you get a lower confidence. So you can see here, it's picking up, once again, this is lens 14F, and we're getting a good confidence through that area. And it's also, there's a bit of a lateral offset here with these lenses, and that's down about 300 meters, but this we were quite happy with. And that's the same location where we saw that empty anomaly. And we're kind of excited about this, and it's something that we're actually going to start another survey in a couple weeks to continue on this grid. So it's quite a positive result for us. So once again, in this slide, just getting near the end here, this one includes our production at the mill from year to year. So we're running about 1.5 million tons, and you can still see that as long as these yellow bars are above the blue bars, then we're keeping ahead of the curve. But when we get below here, then we're starting to lose out a little bit. So when Raglan started out in 1997, production, the mine life was 15 years, and we've been in production for 20 years, and we still have another 15 years to go, unless we don't find anything else. And that's all I have.
Oh, not for you.
Okay. Go ahead.
What was the conductance of the
it was kind of interesting because we had a bit of a pool, and it wasn't really about the conductance, but we had a pool to see what the eventual size of this thing was going to be, and I said like 1.5 million tons, and one of our other geophysicists said 3 million. He won that, so. The highest conductance I've seen at Raglan is about 120,000 siemens per meter, and that stuff is 30 to 50,000, somewhere up in that range. So that's pretty typical for us. Sudbury, we get up to 80 to 100,000. Our deposit our former deposit in Australia, Cosmos, we were seeing those same sort of conductances. So it's nickel sulfide in the Archean. It's pretty much the same in Canada as in Australia. I don't know why the Australians don't use more on-time systems to do exploration for nickel sulfides. That's my pet peeve.
So if at some point, whether you or your predecessors would do the comparisons between the off-time and the on-time to establish this characterization, the only place that I'd seen that this sort of work was Voisey's Bay. Mm-hmm. Maybe because it was all kind of done, the digim and the geotem were done, and the utem.
That's a good suite of data there.
Yeah, but it was done in a compressed time frame too, which may help. Whereas yours has been drawn out over quite a bit longer period of time. So the argument used to be made by your predecessor Tony that the off-time systems, you wouldn't see anything with targets that high a conductance. And is that something which is still a de facto belief on the part of the people working at Raglan, that if you did run an off-time system over these very high conductance bodies, is it you see something but it's not interpretable, or either invisible, or yeah?
So I was talking to Keith Fisk a couple of days ago on the floor. He used to work for Geotech. So he flew V10 for us over the Kamanga deposit.
Right.
And I said, no, kid, there wasn't a halo there, that we didn't see it. So in the case where you have a very high conductance ore body with no halo around it, with no disseminated sulfides around it, you can't be blind to it with some of these airborne systems.
Could be invisible.
Oh yeah, it is. Yeah. It is invisible. I'm not allowed to present that though, so.
Thanks, that was really interesting. Actually, on the same topic, can we go back to that aerotem slide?
I don't know. Can I?
I was just wondering, are those profiles from the on-time channels?
Oh, sorry, yeah, they were on time, yeah.
So that one that you mentioned, where there was no response, or was it kind of in the middle?
Oh, it's probably a little bit too deep, and it's a bit oblong, so
okay.
It's possible that.
So it's not that it's significantly higher conductance than the other ones around it, just maybe depth orientation.
I guess the takeaway I had from reviewing all the airborne data, and it wasn't just the ones I presented, everything was just a mishmash, and I don't really look at the airborne data because since I've only been there 5 years, but we're looking deeper and deeper. So I haven't really gone through the airborne data and picked all these anomalies, because everything I've shown you, it's all been drilled off from surface, and so I don't really have any interest in reviewing it. So. But I kind of thought the 1950, it was kind of cool just going through that data. I started this as a geophysics life of camp for Raglan. And it's just cool. All this data is available on the MERN, the government websites. You can download and have a look at it. But I was really interested just seeing the 1957 survey and just bringing these PDFs and registering them in geoscience analyst and spinning them around. It's pretty cool.
Do you have any case studies of ground TEM with relatively high frequency on time versus, say, a quarter of a hertz squid?
Yeah, so I think we had your system up there to run over the same area, and we've got some good results with that, yeah.
You can't show that, yeah?
I could, but I don't have my computer with me. But so that was more of the problem with Raglan, of course, is the conductive sediments, as you know, and you have the same problems with our neighbors. So what I found interesting with the La Montagne stuff was just using that sort of methodology, instead of just doing standard moving loops, doing the multi-step coverage, we're able to get rid of some of that regional response, we think. So, but we haven't tried the low temperature squid just that one time with you, but yeah, it's a good tool as well.
Thank you, Daryl.
You're welcome.
We'll have a quick break for coffee and we'll be back.